Hello dear students, welcome to the channel and welcome to this playlist in which we are discussing about 8085 microcontroller. We are discussing about the whole microcontroller in detail. We are going to discuss about the programming in it, and we are also discussing about the architecture and pin diagram of it. In previous class we have discussed about the memory organization and the classification of the memory in 8085 microprocessor. Sorry, we are discussing about 8085 microprocessor, not controller. And uh, I have request from many of you to go back a bit and discuss about the pin diagram because many of you have missed that class. So today we are going to discuss about the 8085 pin diagram and the functions of different pins in detail. So in case if you haven't checked out the previous videos, the link will be flashing in the I button on the top right hand side corner of your screen. You can click on it and check out those videos. You can take this video as completely separate video and you can watch it independently as well. So without wasting any time, let's get started with this. So here you can see it is a pin diagram of 8085. Basically 8085 has total 40 pins, and and it works on a single power supply only. And we can also divide these pins in different small classes or small groups based on the application they solve. So you can see here we have divided it in 1 2 3 4 5 6 7 8 classes, starting from serial input output signal. We have interrupt signals, there is a reset signal, clock signals which we give in the beginning, there is address bus and data bus. We have control and status signals, and then peripheral initiated signals, and of course there is a ground signal which uh, I missed in case. So this is the basic pin diagram of 8085, and it starts from x1 x2. Those are the pin number 1 and 2. As you can see here, we have mentioned the pin number as well. Here 1 and 2, x1 and x2, which are the clock signals, or you can also say input clock signals. Then comes this the reset signals, then serial input output ports. Just see the numbers over here. We have reset out as 3, then serial input 4, serial output 4, serial input 5. Then we have the interrupts at 6 to 11. Then the address bus starts from 12 to 18, and then uh, from 18 we have from 1920 we have the ground signals. You can see here we have ground signals at 20, and then from 21 we again go on with address bus 20 21 to 28, and 29. At 29 we have this control status signal starting, and it goes till 31 or something. After that we get our read write signals, like it goes till 33. All this control and status signals go from 29 to 33 around something. And after that we get ready, reset, in, and other signals. From 35 we get peripheral initiated signals till 39, and in between also notice that reset in comes in at 36, right? So reset signal interrupts the peripheral initiated signals, and it goes till 39. And 40th is again, of course, is VCC or power supply, which you can see here. So that is the basic pin diagram. Let's discuss about each of the pins in detail. So first, which I wanted to discuss about the pin would be the address bus and the data bus. Very basic and very easy to understand. So there are output triangle signals and They use the signals are used as higher order 8 bit of 16-bit address. So these signals are unidirectional, which means the address is given by 8085 to select memory as an input output devices. Okay, so basically the highlight is that A to A18 are the outputs tri-state signals which are used as a higher order 8 bits of 16-bit address. So where do we store the lower order 8 bits? So it goes from AD0 to AD7. Okay, so 87 0 to 87 is the lower order 8 bit address of 16-bit address in multiplexer or uh, data, right? So AD0 to AD7 are either address or data bus. You can store either address or data in it. And again, similar to A to A15, these are also input output tri-state signals which have two set of signals, but they needs the demultiplexer. And in an operation cycle during the earlier part, it is used as a lower order address in the late in that part, or we can also use it to store the data as a data bus. Then we will be moving forward to the control and status signals. So note that we are starting from here and going here. Let me change the slide. Yeah. So then we get control and status signals. The first one in the control and status would be the ALE. ALE stands for the address latch enable. It's an output signal which is used to give information of AD0 to AD7, information of AD0 to AD7 contents. And it's a positive going pulse generated during the first clock cycle of the machine cycle. I think it would be better if I can demonstrate it with the drawing, which I probably would do in the next class when we discuss the machine cycle in detail. Now in that, when pulse is high, it indicates that the contents of AD0 to AD7 are address. When it is low, it indicates they are data. And ALE signal is used to separate the AD0 to AD7 to A0 A7 to D0 D7. It means it differentiates if whether my AD0 to AD7 bus is having data inside it or having the address inside it. It cannot have both at the same time. Okay, so if you are thinking about, oh, can't I use 4 bit for address and 4 bit for data? No, you cannot do that, right? So ALE works as a multiplexer, demultiplexer, sorry, and it is a latched control signal. Then we have input output memory, which is an output status signal which is used to give the information of operation to be performed with the memory or input output devices. And the microprocessor is performing a memory related operations. Then we have the status signal. Status signal are the output status signal used to give information of operation performed by microprocessor. We use S0 and S1 notation, which is line specific for different conditions of 8085 machine cycle. It can be 00, 01, 10 and 11. 11 stands for opcode fetch or instruction from read memory. 01 stands for read only. 10 stands for write only, and 00 stands for halt. And based on that, we can also form this machine cycle status chart, which we will be using in the upcoming lectures in order to draw the timing diagrams of different instructions which we will be studying. So you can see is 1 is the opcode fetch, 00 is halt, 1 is interrupt, and also this input output memory also plays its part. When it is 0 and S1 and S0 is 1, that means opcode fetch. When it is 1, and S1 and S2 is 1, that means interrupt acknowledged. So it serves different purposes which we will be studying. No need to go into the detail of this right now, but we will be moving and discussing about it in detail in upcoming time. Then in the status signal and control signal only, there is read, which is active low output control signal used to read the data from the selected memory location or an input output device or port via the bus. There is a write who performs similar operation, write WR, which is an active low output control signal used to write the data to select a memory location or an input output device or port via data bus. Then we would be moving to the ready, the last one, which ready is something that we discussed about in previous class as well. So we'll not go into the too much detail, but let's discuss it still. This is an active high interrupt control signal, which is used by microcontroller to detect whether the peripheral is ready for the data transfer or not. If not, the processor waits till the signal goes high, and the main function of this pin is to synchronize the microprocessor with slower peripherals. Right? We discussed about it earlier. Then we will be moving to the third one, interrupt signal. The first signal of the interrupt signal group is the trap signal, which is again an active high level and edge triggered non-maskable high priority interrupt. Don't worry about the wordings. If you don't understand, we will be using it when we will be uh, going with the machine cycles, different instructions, right? So for now, just understand that when the trap line is activated, microprocessor performs internal restart automatically at the address 0024 or whatever address. Then we have the reset instruction. Reset reset interrupts. The reset interrupts, see, it goes from 5.5, 6.5 and 7.5, as you can see here. So they are all again active high signals, triggered and maskable interrupts, and they cause it internal restart to automatically inserted, and the priority goes from 7.5, then 6.5 and 5.5. So if 7.5 is activated and 6.5 is also activated, then first 7.5 will be executed. When this RST 7.5, 6.5 and 5.5 is active in microprocessor performs internal restart automatically at address 003CH, 0034H and 002CH respectively for 7.5, 6.5 and 5.5. After this restart interrupts, we have INTR. You can see pin number 10. It's also an active high level triggered general purpose interrupt, but it has the lowest priority, right? So this is something that would be executed the last. Then we have INTA, which is used to indicate the microprocessor has received an INTR interrupt or not, right? So it is used for indication purpose only. Then the third one we have is the DMA request signals, and the what comes in the DMA request signal, or you can also call it the peripheral initiated signals, hold and HLDA, and sometimes you put ready in it as well. So we've discussed about these signals earlier as well. Hold is an active high input signal used by other controller to request the microprocessor about the application of the data, address, and the control signals via whatever bus. All three of these bus, of which we have discussed in the previous class. Then the the microprocessor the microprocessor in response to hold generates a signal to acknowledge the requesting device by HLDA signal. Now when HLDA is active, it indicates the microprocessor has received hold request and will relinquish the buses in next clock cycle. So the other controller will be using the buses, and upon completion of the work will remove the hold signal. Because of this, microprocessor will also make HLDA low, and it takes the control of the buses half clock cycle after HLDA goes low. So that's HLDA and hold. Then we have the two reset signals, reset in and reset out. So reset in is an active low signal. It's input reset signal. So when reset in command is equals to 0, or means whenever it is low, it clears the program counter till 0000 and makes address, data and control lines tri-stated. So after the reset, the status of the internal register and flags are unpredictable. The CPU is held in the reset condition as long as the reset in is applied. And after the reset of microprocessor, it starts executing instruction from 0000H onwards. Right? So use reset very carefully whenever you have to use it. Then we have the reset out, which is an active high output signal which is used to indicate the microprocessor is reset. And this signal is used as a system reset to reset other devices connected in system. Then we have the serial input output signals. It's an active high serial input port pin used to accept the serial 1 bit data under the software control. And this I'm talking about the serial input only. Okay, serial output we will be discussing later. So serial input is an active high port pin used to accept serial 1 bit data under software control. And when RIM instruction is executed, the SID or the signal serial input data pin loads the data into D7 bit of accumulator. Then we have serial output data or SOD pin. It is also an active high pin serial output port used to transfer serial 1 bit data under software control. And when SIM instruction is executed, the signal output data serial output data pin is set or reset depending on the D7 and D6 bits of the accumulator. After serial, we have the simple clock and power signals. Clock signals are X1, X2 and clock out. X1 and X2 are the input signals which are connected to the crystal LC or RC network. As you can see here, they are connected to LC or RC network. The X1 and X2 pins drive the internal clock generator circuit. The frequency is divided by 2 and used as operating frequency. Generally 6.014 megahertz crystal is connected to X1 and X2, and this is divided by 2. So the operating frequency of 8085 microprocessor is 3.07 megahertz. Then we have the clock out signal. See the 37 number pin. It's an output signal which is used as a system clock. The internal operating frequency is available on clock out pin. Right, it can vary sometimes. Then we have the power signals VCC and VSS, which provides the power supply. VCC plus 5 volt, and then we have the ground signal VSS, simple ground reference. So that was the pin diagram of 8085 microprocessor, except that there is one thing which I wanted to discuss as well. So in previous class when we discussed about the registers, I told you that I will be discussing about the flag register in upcoming time. So I want to discuss about 5 of those flag registers. So let's get to it. So basically flag is a flip-flop. It indicates some instruction executed by my microcontroller. micro So The flag register of 8085 microprocessor consists of 5 flags, uh, and flag register is connected to my arithmetic latch unit, arithmetic logical unit ALU, and when the operation is performed by ALU, the result is transferred to the internal data bus, and status of the result will be stored in the flip flop. Now there are five different flags. First one is the carry flag. So this flag is set whenever there has been a carry out of or borrow into the higher order bit of the result. So flag is used by the instructions and that add and subtract the multiple multi-byte numbers, and it rotate instructions can also isolate a bit of memory or a register by placing it in the carry flag. So one if there is a carry out of or of the most significant bit, and zero if there is no carry from my MSB. Then we have parity flag, which will be set when the result has even parity, as even number has one bit, and if parity odd, then parity flag will be resettled. The flag is normally used to check the data transmission errors. Then auxiliary carry flag, which will be set whenever there has been a carry out of low nibble into the high nibble of a borrow, or borrow from a high nibble into the low nibble of an 8-bit quantity. So low order byte of 16-bit quantity, and except that the auxiliary carry will remain reset. And this flag will be used by the decimal arithmetic instruction. Then we have zero flag, which flag will be set when the result of the operation is zero. Accept it, it will be reset. And then we have sign flag, which will be set when the higher order bit of the result is 1. And since the negative binary number are represented in the 8085 8086 CPU in standard 2 uh, standard standard 2's complement, so this sign flag will be using it as a indication or indicator of that. So if MSB is 1, which means my number is negative, then sign flag will be activated. So let's keep it till here today. If you have any doubts or any questions, please mention them in the comment section below. If you have any feedback related to the channel or lectures, please mention them in the comment section below as well. Please mention whatever you want me to make video on. I'll be seeing you next time. Till then, thank you very much for listening. Goodbye for now.